Okay, today we're going to cover 14.1, the nature of stationary points, and we'll learn to describe the behavior of functions around stationary points to define coordinates of stationary points and determine their nature. So, first and foremost, just some context. Why in the world do we need to find these nature of stationary points? Okay, in real life, be it in manufacturing, engineering, or logistics, you would want to find the maximum or minimum value. So, for example, given some metal, okay, let's say if you want to make a drink can, I know the cans that we have, like the Coca-Cola and Sprite cans. So, for the given amount of metal that we have, okay, we will want to maximize, right, the possibly the volume that we have, given the amount of metal that we have. So this is a problem of optimization. So we want to have the maximum value of a certain volume, so to speak, and we can actually use calculus, right, to actually solve. So in this chapter, we apply differentiation to find the maximum or minimum value of a variable in practical problems, such as the maximum area of a rectangle given a fixed perimeter, or the minimum surface area of a solid given a fixed volume. So this part here was about the drink can I was talking about earlier. So now, first and foremost, what are stationary points? Okay, so stationary points are here and here given this graph. Okay, so basically stationary points, right, are, if you think about it, if you are walking up a hill, at the top of the hill itself, okay, if you were to measure the gradient down here, it is 0. So this gradient here is flat. Similarly, okay, you continue walking downwards until this lowest point here. And this lowest point here, if you measure the gradient at this point, you draw a tangent at the point, you find that the gradient here is 0 as well. So A and B are known as what I call stationary points. Okay, now if you recall, in this case, this here is a peak, so A is actually a maximum point, okay, while B itself is actually over here, so it is a minimum point itself. So now we have an idea of stationary points can be a maximum point or minimum point. Later on the chapter, we also find it's a third kind of stationary point called a point of inflection. But never mind, okay, once I show you some examples, I will show you the point of inflection later on. So the very first concept that we learned, that for stationary points, okay, it has 0 gradient. Take note of this. This is the important concept going into the first example. So in example 1, what we have here is this. It shows the curve y equals to 2x cubed minus 9x squared plus 12x minus 5. And this example is very nice to you. They actually show you the curve itself. Most of the time, we won't show you the curve, we just ask you to actually find the stationary points. So without much further ado, part 1, she tells us to find, you differentiate y with respect to x. So this one is a simple enough question. I think we've done this enough times for you to be able to do this very quickly. So what we get is 6x squared minus 18x plus 12. Okay, now the coordinates of P and Q. P and Q are stationary points. So based on the previous concept that we've learned, at stationary points, we know that if we differentiate y with respect to x is equals to 0. Basically, the gradient at stationary points is equals to 0 itself. So very quickly, 6x squared minus 18x plus 12 is equals to 0. Let's make our life a bit easier by dividing by 6. Very quickly now, let us just go and factorize. So the x value equals to 1, or the x value equals to 2. Now, okay, we got x equals to 1, x equals to 2. Our question is still not done yet. So copying from the previous slide, x equals to 1, x equals to 2. We still have not solved for P and Q. So to get my y value, I will substitute my x value into the equation down here. So therefore, y equals to 2 times 1 cubed minus 9, 1 square, 12, 1 minus 5. And I find that my y value in this case is equals to 0. Therefore, the coordinate of P is equals to 1, 0. Similarly, to find the coordinate of Q, okay, I will substitute in the x value is equals to 2 into this equation here. And in this case, I find that my y value is -1. Hence, the coordinates of Q is equals to 2 and -1. So that quite simply is example 1, using the concept that at stationary points, dy dx is equals to 0. Now, okay, please pause the video and try 1. If you want to use your textbook, this can be found in your textbook on page 48 itself. And I will carry on in 3, 2, 1. Okay, if you had differentiated, you will found that differentiating y respect to it gives you 6x minus 6. There's actually no need to go and factorize, but this is what the answer key gives. Okay, now the main concept here is that at stationary points, the gradient is equals to 0. So solving, you get x equals to 1. To find the y value, you substitute back into the equation of the curve itself. You find that the y value is -2. So I would think that you could have simply got that the coordinate of stationary point is 1, -2. Not a very difficult try one. Okay, now back to stationary points. Okay, so what we have here is this. The stationary, there are 3 different types of stationary points. Earlier, I already spoke about 2 already, the maximum point. So based on this example that's given in your textbook on page 49 itself, A itself, it goes up, it's a crest. So A is a maximum point. Similarly, for B, it goes down this way. Okay, so B is a minimum point. Last but not least, there's something new, which is C. So point C itself, okay, I will just trace out the shape here. Okay, point C, if you were to measure the gradient at point C, you draw this, you'll find that the gradient here is equals to 0. However, you notice here the gradient is positive. To the right of the point, the gradient is positive. For points A and B, it will be positive, 0, negative. Or for point B itself, it was negative gradient is 0, then positive gradient. For point C, notice that the gradient is positive, then 0. It doesn't change to negative, it carries on being positive. This is a special kind of stationary point known as a point of inflection. Okay, so this is what we have in point C itself, which is a point of inflection. So these are the 3 different points: the maximum point, the minimum point, and the stationary point of inflection, which was shown by point C in this example itself. So now, to determine whether a stationary point is a maximum, minimum, or point inflection, we will have something called the first derivative test. So in the first derivative test, okay, it can be shown like this. So basically, what we will do is we will actually try to find a value that is to the left or to the right of the point itself, and to see whether the gradient is negative or positive. And then from there, we will infer the gradient, and then we'll try to sketch the shape of the graph, and that sketch itself will actually show us whether it's a maximum point or a minimum point. So for example, okay, for a minimum point, to let's say point P, to the left of the point itself, the gradient is negative, it's going downwards. At the point itself, gradient is 0. To the right of the point, the gradient is positive. So it is negative, 0, positive. If you were to sketch the shape of the graph itself, you'll notice that this is actually a smiley face, so it is a minimum point. Similarly, for a maximum point itself, to the left of the point itself, the gradient is positive. at the point itself, gradient is 0. Then to the right of the point itself, gradient is negative. You sketch the graph, you get this, and what this shows that this is a maximum point. Lastly, for point of inflection, it can be negative, 0, negative, the graph shape is like this, or positive, 0, positive, graph shape is like this. So that will give you a point of inflection. So the gradient slightly to the left and the gradient slightly to the right of a point will help us to actually determine what kind of point it is, whether it's positive, whether it's maximum, minimum, or whether it is a point of inflection. So now, okay, don't worry about it. I've spoken quite a bit about this. Let's just look at example 2 itself. So for example 2 itself, what will happen here is that we will actually have the curve has two stationary points. So first, what they want us to do in example 2 is to find differentiate y with respect to x, and to show that it's given with that expression over there. So if I start to differentiate, what I get is 6x squared minus 12x minus 18. Now what I can do is to factorize 6. I get x squared minus 2x minus 3. Then if I factorize, I get x plus 1, x minus 3. Quite a simple part 1 I have shown, okay, that this is dy dx. Now part 2 is to consider and to find the stationary points. As we have learned in the earlier example, to find the coordinates of the stationary points, what I want is to find where dy dx is equals to 0. So given that I've already had this very nice what I call expression over here, so I just equate that to 0. So x value is negative 1, or my x value is equals to 3. Now if I want to find my y values, I will use the equation of the curve itself. If I substitute in here, I just do it for negative 1. The other one I'll just give you the answer. Negative 1 square minus 18 times negative 1 minus 5. You use your calculator, and what you'll find is that your y value is equals to 5. So similarly, for x equals to 3, you substitute that into your graph, into your equation of the graph itself, or the curve rather. You find that your y value is equals to negative 59. So hence, okay, the coordinates are negative 1, 5, and 3, negative 59. So I found my coordinates of my stationary points. Now part 3 is the new one, okay. By considering the sign of dy dx, determine the nature of these 2 points. Okay, here we go. Now, okay, so we have already found the 2 points, negative 1, 5, and 3, negative 59. Okay, so now what we're going to do here is this. When we use a first derivative test, you need to draw this table here. Okay, so no need to use a ruler, no need to be so nice and all. Okay, but basically, right, you just use a rough sketch there. What you need is x, the sign of dy dx, the sketch of tangent, and the sketch of the curve itself. Okay, now what is negative 1 minus? Negative 1 minus is a point slightly to the left of negative 1. So let me help you here. If I were to draw, okay, a point, negative 1 is a number line, something slightly to the left of negative 1 will be negative 1.1, okay, and something slightly to the right of negative 1 is negative 0.9. Okay, so far so good. Okay, now just to remind you all of what dy dx was. So if you recall from the earlier part, my gradient function dy dx is 6x plus 1, x minus 3. Okay, this will factor in quite importantly for us now as we try to find the sign of dy dx. Okay, now what we're going to do here is this. using x equals to negative 1.1, or what I've written here, negative 1 minus, this is a notation showing that I'm using a value that is slightly to the left of negative 1, or something slightly more negative than negative 1. So I substitute negative 1.1 here and negative 1.1 here. If you were to use your calculator, okay, when x is negative 1.1, what we will get here is equals to 2.46. So the gradient here is greater than 0. Greater than 0 means that this is a positive gradient. So slightly less than negative 1, okay, the point here, it is a positive gradient. So here I write here it is a positive sign because we had 2.46 earlier, and the sketch of the gradient is positive. This one, okay, here, no need to do. Why? Because I know there's a stationary point, so at this point here, the sign of dy dx must be 0. You know, something wrong already. Okay, the sketch of the tangent at this point here will be a flat. Now negative 1 plus, that means something that is slightly to the right or slightly more than negative 1. So here the value we use is negative 0.9. Once again, using dy dx, okay, you use 6 0.9 6 negative 0.9 plus 1 negative 0.9 minus 3. Then the value that we will get down here, okay, you will find that the value here will be negative 2.34, which is less than 0. So if it's less than 0, okay, what we know that the sign of dy dx is negative. So this is negative, and this will be the sketch of the graph. So here what we get is negative. Here, okay, the sketch of the graph will be going downwards, which is negative. So if you join the dots, so to speak, you'll find that the sketch of the graph will be like this. So if it's like this, okay, it's from positive to 0 to negative. So what I can conclude here is negative 1 and 5 is since it crests upwards, it is a maximum point. Okay, let's rinse and repeat this for 3 and negative 59. So once again, let me write it out. Dy dx earlier we found to be 6 times x plus 1 and x minus 3. So again, the x value is 3. Slightly to the left of 3, I can probably use 2.9, and slightly to the right of 3, I can use 3.1 itself. So doing the same method there, if you use 2.9, you substitute this into your gradient function itself, you'll find that the value is something that is negative. So the sign of dy dx here is negative. At the point itself, this is a stationary point here, dy dx is 0. And if you use the value of 3.1, you substitute into the gradient function itself, you will actually find that, hey, in this case, the sign of dy dx is positive. So now if I were to sketch my tangent, negative tangent is a downward sloping line like this, 0 tangent is a flat line, positive is a upward line like this. So if you join the dots, you will see that it will give you this. Hence, okay, this is clearly a minimum point. So the statement I can make here is, 3 negative 59 is a minimum point. So basically what I've done here is I have determined the nature of these 2 points. So the nature meaning, is it a maximum point or a minimum point itself? So now I urge you to pause the video and try to, and once you are done trying this, and you can unpause the video and I'll present the answers to you in 3, 2, 1. Okay, First, if you had differentiated, you will find that this is what you have differentiated, and you express it in the form 6 times x minus 1 x minus 2, because they wanted you to show. Okay, so this one is actually shown. Now, at stationary points, as we have repeated over and over again, dy dx equals to 0, you solve x equals to 1, x equals to 2, so you sub the x value in to the original equation of the curve. You find the y value is 1, and when x is 2, the y value is 0. Hence, the stationary points are 1, 1, and 2, 0. Now, okay, we need to determine them. So if I were to use, okay, the first derivative test for 1, 1, okay, once again, 1 minus is something slightly to the left of 1. So I can use the value of x equals to 0.9. This one is probably something to the right of 1.1. X is right of 1. So x equals to 1.1. You notice that sign of dy dx is positive, 0, and negative. Hence, okay, positive is upward, 0. Negative gradient is downwards, so you join the dots, you find that this is a hill. Okay, so 1, 1 is a maximum point. Similarly, for 2, 0, here, something to the left of 2 will probably be 1.9. Something slightly to the right of 2 will be 2.1. You must only use values that are slightly to the left and slightly to the right. If not, it will be somewhere else on the curve already. So you must use something slightly to the left, something slightly to the right. You will find that, okay, is negative, 0, and positive. So if I were to sketch negative, 0, positive, join the dots, it's a smiley face. Hence, okay, 2, 0 is a minimum point itself. Now, this is the final example for this part 1. Okay, then I'll pause, I will stop this video, so that the next video will talk about the second derivative test. So now, first and foremost, once again, rinse and repeat, we will try to find the value of dy dx. So, okay, dy dx in example 3, applying the chain rule, 3 x squared minus 1 square, and I have differentiate what's in the bracket is 2x. So if I simplify this, I get 6x x squared minus 1 square. Now, determine the nature of all the stationary points of the curve. So now what I need to do is to actually find the stationary points. So again, okay, at stationary points, I know that dy dx is equals to 0. So 6x x squared minus 1 square is equals to 0. So if I start to solve, 6x equals to 0, or x squared minus 1 is equals to 0. Hence, x equals to 0, x squared is equals to 1, x equals to 1 or negative 1. Now I will just shortcut this. If I had used my original equation over here, I substitute it in my x values, which I found below. I can find the corresponding y coordinates. Okay, so when x equals to 0, I know that my y value is 2. When my x value is 1, my y value is 3. And when my x value is negative 1, my y value is also equals to 3. So therefore, my stationary points have coordinates 0, 2, 1, 3, and negative 1 and 3. So this is just things that we've been doing over and over again in the previous view. So now, what I'm going to do here is this. Okay, I will use the first derivative test, okay, on all 3. So remember that we have a negative 1, 0, and 1. So once again, I just focus on negative 1. When x is value negative 1, something slightly to the left of negative 1 would likely be negative 1.1. Something slightly to the right of negative 1 will be negative 0.9. If you have trouble with these values, you may choose to use a number line to help you to ascertain what values you can do to put into dy dx. And in this case, you'll find that at negative 1.1, slightly to the left of negative 1, it is a negative. It's on the point itself, it must be 0. This is a stationary point. To the right of it is negative. So if you sketch the tangent, negative, 0, negative, what we have is this. This clearly is a point of inflection. Similarly, for point 1, 3, I won't belabor the point. So what we get is positive, 0 and positive. This point 2 is a point of inflection. Lastly, for point 02, for point 02, slightly to the left of 0 maybe is negative 0.1. Slightly to the right of 0 will be positive 0.1. The sign of dy dx is negative, 0 and positive. So negative, 0 and positive, you join the dots, you get a curve that looks like this. So the sketch in this case indicates that this is a minimum point. So if I put all of it together, negative 1, 3, negative and 1, 3 are stationary points of inflection, or you can just state that they are points of inflection, and 0, 2 itself is a minimum point. Now, what you need to do is to pause the video, try 3, okay, and then once you are done trying this, okay, you may unpause the video and present you the answers in 3, 2, 1. Okay, differentiating, applying the chain rule, you get this, and then if you simplify, you get this. Okay, that's it for part 1, simple enough. 6x squared x cubed minus 1. Now, okay, at stationary points, dy dx equals to 0. If you were to solve this, 6x squared equals to 0, you find that x equals to 0, x cubed equals minus 1 equals to 0, you find x equals to 1. So this question slightly less complicated. There's only 2 stationary points. My example had 3. So when x equals to 0, your y value you sub into the original equation is negative 2. When your x value is 1, sub into the original equation, you get negative 3. So you have 2 stationary points, 0, negative 2, 1, and negative 3. So if we use the first derivative test for 0, negative 2, slightly to the left, negative 0.1, slightly to the right, 0.1, you'll find that it's negative, 0, negative. So you sketch the tangent. What you have is this, it's a point of inflection. Similarly, for 1, negative 3, slightly to the right of 1, use 1.1, slightly to the left of 1, maybe a 0.9. So if you put into dy dx, what we had earlier, what we have is dy dx is negative, 0, and positive for the corresponding values of x that you put in. So you sketch the graph, you sketch the tangent, it is clearly a minimum point. So now you can make your final statement. 0, negative 2 is a point of inflection, and 1, negative 3 is a minimum